Hi everyone, my name is Aaron, and recently I made a game with my friend Thomas. During the last weekend of 2024, we participated in the Winter Melon Jam with the theme of polarity. When the theme was first announced, we played around with a few ideas, including electrical polarity and political polarity, but we knew that the most popular idea would be magnet-focused puzzle platformers. So we tried to stay pretty far away from that, and took some inspiration from the Dune franchise. Now you might say, Aaron, that's only because you have a Dune sword on your wall, or because you got the Ornithopter Lego for Christmas, or because Dune Parts 1 and 2 are your top 2 movies and your best movies of all time list. And to that I say, come on man. Specifically, we focused on the section of the first book, where the Atreides begin to take over Arrakis and worry about the supply of water contained in the ice caps of the North Pole. Additionally, we looked at the scene playing here for the visual design of the game. And with that, Helmeteers was born, an RTS where you and an AI opponent battle over a fake resource on the poles of a fictional, randomly generated planet. We first worked on making the level generation for the planet. So we start off with a circle of grass created with Unity's tile map system. We then try to make it a little more interesting and more applicable to the theme by adding the poles of the planet. This is done by calculating the distance from each tile to the nearest pole and setting the ones under a certain threshold to snow. Similarly, we set the area around the equator to sand. We found that a flat band around the planet looked pretty sad, so we also took the distance to the nearest pole into account to give it that bend around the middle. We then move on to something a little more interesting. Using the Perlin noise algorithm, which I'll talk a little bit about later, we place the fictional resource of never-findium around the planet and focus it almost exclusively around the poles. Using the same method, we place obstacles like water and rocks around the planet to make pathfinding just a little more difficult. Finally, we place the control points you'll be looking to capture randomly throughout the planet with a minimum distance between each. As shown here, the control points are used to generate a control map around the entire planet, which looks like a Voronoi diagram if you've ever seen one. Areas you've conquered show up in blue, while areas the enemy conquers show up in red. You can only place buildings to reinforce your soldiers in the blue areas, which forces you to use a little more strategy when attacking. Now, I want to talk about the Perlin noise algorithm for a second, since I've used it for a few projects previously and only recently decided to dive into the actual algorithm. Perlin noise was invented in the 80s by Ken Perlin and actually won an Oscar for its use in the original Tron film, unlike Tron Legacy, which was robbed at the Oscars. For Perlin noise, you start out with a grid of points. Here I'm using a 3x3 grid with 9 points, but it's implemented on an infinite plane. You then draw what's called a gradient vector at each point. These vectors are just groups of 2 numbers with a combined length of 1. I'm using 1 and 1 for the example vector because it's going up and to the right. It technically has a length of about 1.4, but I'll ignore that for now. You repeat this for each point. The vectors seem random, but actually use a set of 256 predetermined vectors defined in a permutation table. These can change with different implementations of the algorithm. You then find the position you're looking for, which I'm marking with green. You take the 4 grid points around the screen point and find the difference between their positions, called an offset vector. For each of these grid points, you calculate the dot product between its gradient vector and the offset vector to the green point. The dot product is just the sum of the products of the elements of the 2 vectors, which I'm writing out here. After doing this for all grid points, you take a weighted sum of the dot products, where grid points closer to the green point contribute more to the output. So that's for 1 point, but how about using Perlin noise in practice? Here's a single line with 100 points. At each point, we increase the position of the target point, which I previously showed in green, into the Perlin noise map. After finding all the values for each position, it looks pretty cool and gives us a smooth but random curve. However, most of the time, one line isn't enough to make terrain look realistic. That's why we use multiple lines, called octaves, to make the final output more interesting. Each octave is given a different scale or level of detail. Ones with higher scale look more jagged because the position of the point in the noise grid is moving faster. Now we don't want the jaggedness of the higher scale octaves to drastically change the output, so we scale them down using an amplitude value based on the level of detail. Finally, we take the sum of all the octaves at each point to create the output. Using all of that, for each tile with a noise value above a certain threshold, we set it to either never-findium, water, or stone. We then moved on to building placement. We create a resource collector and 3 types of barracks for different soldier classes. When you select a building, a transparent version of the building appears to preview your selected spot. You can place resource collectors on a deposit of Neverfindium to start collecting the resource. Placing the barracks starts the clock for spawning soldiers. Placing buildings depletes your Neverfindium supply, which can prevent you from placing other buildings. Invalid placement due to location or lack of resources is displayed in red. The resource collectors also have a neat visual indication of their output, where the amount of particles emitted is dependent on the number of resource tiles in its range. To create the buildings, we used Unity's scriptable object system. Creating a scriptable object allows you to store groups of data in an asset when multiple slightly different objects need to be created. The script adds a new item that you've defined to the Create menu, which you can then modify and use in your scene. Here are some of the prefabs we've used for our buildings. They all contain the same script that allows soldiers to target and destroy them, and they each have a script that defines their specific purpose. After working on building placement, we built the individual soldier movement. In Helmetiers, you have access to a selection box that can pick out soldiers. By right-clicking on a position, all selected soldiers automatically pathfind to that position. Here I'm trying to capture a control point by sending a group of my soldiers to a nearby location. Once they get near the target, they each move to a randomly offset position to prevent clumping. To create the pathfinding, we use the A-star algorithm, which I'll show here. But first, I need to show a simpler pathfinding algorithm that forms the basis for A-star, called breadth-first search, or flood fill. I've created a small environment here, with a starting point colored in blue and a goal in green. Breadth-first search uses a queue, where you add tiles and take them off in the same order. A queue is the reverse of a stack, if you've ever used that. You start with the initial tile in the queue. You then remove the initial tile from the queue, visit all of its neighbors, and add each of them to the queue. After that, you remove the first tile in the queue, add any of its neighbors that haven't already been visited, and repeat this process, adding and removing from the queue until you find the goal. By keeping track of which tile preceded every tile in your search, you can trace your steps back from the goal to the starting point and find the optimal path through the environment. While breadth-first search is guaranteed to find an optimal path, it unfortunately explores many dead ends and suboptimal routes, which limit its efficiency. Because of this, we turn to A-star. Similar to breadth-first search, A-star also uses a queue to store the tiles, but it uses a min-priority queue, also called a heap for some reason. Using this, instead of retrieving the tile that was put into the queue earliest, the priority queue retrieves the one with the minimum priority, which does seem a bit backwards. For A-star, the priority for each tile is the sum of the current distance traveled and the estimated distance to go. To estimate the distance of the future part of the path, we use a heuristic, which is a fancy word for a simple distance calculation. You can use any distance calculation, but we use Manhattan distance, which is the sum of the difference between the x and y values, as shown here. As in breadth-first search, we continue to add tiles to the queue and remove them. The difference is that we only search the tiles we think could be part of the optimal path, which prevents exploring many dead ends and roundabouts. Putting that into practice, we get the basic pathfinding for our soldiers, but with dozens of soldiers moving at once across a large map, it would be inefficient and cause lag to pathfind tile by tile for each soldier. That's why we create a highway system, where invisible highway nodes, shown here, are placed around the map on walkable tiles at consistent intervals. The highway nodes use raycasting in the 4 cardinal directions and diagonally to find neighbors while avoiding obstacles. This creates a higher view map of the environment that's faster to traverse in A-star. The soldiers simply find the highway node nearest to them that's in the direction of the target position and pathfind to it, making their way along the highway until they reach their destination. To make it even more efficient, we implement a herding system, where soldiers who are near each other and get the same command take the same path. This means that if you select 10 soldiers in the same area, we only pathfind along the highway once, and can just calculate the path to and from the highway for each soldier. If soldiers aren't already locked onto a target, they raycast in a circle to find opposing soldiers and buildings. If they find one within their range that isn't blocked by an obstacle, they fire at the enemy while moving to their requested position. Finally, we can take a look at the enemy's overall AI. Despite all soldiers using the same pathfinding and shooting logic, the opposing team needs some guidance on where to direct troops and where to place buildings. As shown on the right side of the screen with my mess of public variables, the enemy takes many factors into account when determining which control points to target with soldiers. These include the number of friendly and enemy soldiers and buildings in the vicinity, the proximity to control points the enemy has already conquered, and the position of the control point on the planet. The enemy can reorder its priorities once every few seconds, and directs the nearest soldiers to its determined targets in a relatively even distribution. Depending on the amount of resources the enemy has, it can place buildings at different speeds, with an absolute maximum of 15 at a time though. When there was no maximum, it tended to create fortresses or barracks that were impossible to defeat. When the enemy has fewer resources, it tends to place resource collectors to build up its supply. Similar to troop movement, building placement also depends on a number of factors, like position on the planet and proximity to control points that are currently being targeted. I found the enemy is fairly difficult to defeat and takes a high level of aggressiveness. I'll let you all watch them finish their conquest of this planet. So that's Helmeteers. It's free to play in your browser right now on my itch page, which I'll link in the description. There are a few bugs we know about, but the judging period for the game jam hasn't ended yet, so we can't fix them until then. A big thank you to the hosts of the Winter Melon Game Jam and to everyone else who participated. This was a really fun project to do over a weekend, and I'll probably do more like it in the future. Thank you to Thomas for doing half the work on this game, and to my dad Jason for making the music. Thank you all for watching. Please stay tuned in the near future because I plan on announcing a new game for official release on Steam in the coming months that I don't think you'll want to miss. See y'all later.